Hello there, and welcome. Tonight I want to take you somewhere special, somewhere that exists in the quiet spaces between what we know and what we wonder about. As you settle into your comfortable position, perhaps adjusting your pillow just right, letting the weight of the day slowly dissolve from your shoulders, I want to share with you a question that has been whispering through the corridors of scientific thought for decades now. It's a question that might initially seem like pure science fiction, something from the realm of imagination rather than serious scientific inquiry. But I invite you to consider it with me, to let it unfold in your mind like a flower opening to moonlight. What if, somewhere in our solar system, perhaps drifting in the darkness between planets, or nestled quietly in the gravitational sweet spots we call Lagrange points, there exists an ancient artifact, a probe sent by a civilization that was already old when our Earth was young? What if this probe has been here all along, waiting with infinite patience, watching our species emerge from the primordial soup, develop consciousness, build cities, and finally, just recently in cosmic terms, begin to reach out into space ourselves? This isn't just wild speculation, you see. It's a serious hypothesis proposed by one of the most respected scientists of the 20th century. And tonight, as you drift towards sleep, we're going to explore this possibility together, gently, thoughtfully, with all the wonder it deserves. The idea might seem overwhelming at first, perhaps even a little unsettling, but I want you to know that there's nothing to fear in what we're about to discuss. Instead, think of it as we might think of finding an old message in a bottle on a beach, or discovering a time capsule buried by someone long ago. There's something deeply poetic about the possibility that we might not be alone, that someone, somewhere, at some point in the vast history of the universe, might have thought of us, or at least thought of the possibility of us, and left something here for us to find when we were ready. Before we continue, and I know this might seem like an unusual moment to mention this, but if you're finding comfort in this journey we're beginning together, if these words are helping you settle into a peaceful state of mind, I'd love to know where you're listening from tonight. Perhaps you're in a bustling city where the lights never quite go out, or maybe you're in a quiet rural area where you can actually see the stars we're about to discuss. What time is it where you are? Is it late evening, the middle of the night, or perhaps you're listening during a quiet afternoon? If you feel moved to do so, consider leaving a comment sharing your location and the time, creating a little constellation of listeners scattered across our planet, all contemplating the same cosmic mysteries together. And if this documentary brings you peace or sparks your curiosity, perhaps consider subscribing so we can take more of these gentle journeys into the unknown together. But for now, let's return to our cosmic contemplation. The scientist who first seriously proposed this idea was Ronald Bracewell, a brilliant radio astronomer from Stanford University who spent his life listening to the cosmos, trying to decode its secrets. In 1960, the same year that Frank Drake first pointed a radio telescope at nearby stars to search for intelligent signals, Bracewell published a paper that would forever change how we think about the search for extraterrestrial intelligence. He suggested that instead of trying to communicate across the vast distances of space using radio signals that would take years, decades, or even centuries to travel between stars, an advanced civilization might instead send robotic probes to other star systems. These probes would be like cosmic messages in bottles, drifting through space for millions of years if necessary, waiting patiently for a civilization to arise that could recognize them for what they were. Think about this for a moment and really let it sink into your consciousness as you relax. We humans have only had radio technology for a little over a century. We've only been able to leave our planet for about 60 years. In cosmic terms, we've just barely opened our eyes, but the universe is 13.8 billion years old. Our galaxy, the Milky Way, is nearly as ancient. There could be civilizations out there that are millions or even billions of years older than us. To them, we would be like infants just learning to crawl. And just as we might leave a gift for a child to find when they're old enough to appreciate it, perhaps these ancient civilizations have left something for us, something waiting patiently in the darkness. The beauty of Bracewell's idea is its practicality. You see, the distances between stars are so vast that they challenge our human comprehension. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. If you could travel at the speed of light, which according to our current understanding of physics is impossible for anything with mass, it would still take you over 4 years to get there. At the speeds our current spacecraft can achieve, the journey would take tens of thousands of years. But a probe, a robotic sentinel, doesn't mind waiting. It doesn't get lonely or bored. It doesn't age in the way biological beings do. It could drift through space for eons, powered perhaps by the thin sunlight of whatever star it happens to be near, its electronic consciousness dormant but ready to wake when the right conditions are met. Imagine, if you will, such a probe arriving in our solar system millions of years ago, when dinosaurs still roamed the Earth, or perhaps even earlier, when life was just beginning to experiment with complexity in the warm oceans of our young planet. This probe, following instructions written in some unimaginable alien computer language, might have settled into a stable orbit somewhere inconspicuous. Perhaps it chose one of the Lagrange points, those special locations where the gravitational forces of the Sun and a planet balance out, creating a kind of gravitational parking spot where an object can remain indefinitely with minimal energy expenditure. Or perhaps it disguised itself as an asteroid, coating itself in dust and rock, becoming indistinguishable from the millions of other space rocks that populate our solar system. And there it would wait, patient as a mountain, as the Earth spun through its days and seasons, as continents drifted and collided, as life evolved from simple cells to complex organisms, through mass extinctions and explosive diversifications, through ice ages and warm periods, until finally, just in the last whisper of geological time, a species arose that began to look up at the stars with wonder and build tools to explore them. That species, of course, is us. The probe might have been programmed with exquisite sensitivity, able to detect the signs of an emerging technological civilization. Perhaps it noticed when we began to reshape our planet's atmosphere with industry, or when we started broadcasting radio and television signals out into space, or when we detonated our first atomic weapons, briefly outshining the sun in certain wavelengths of light. Any of these might have been the trigger that caused it to stir from its long slumber, to begin observing more closely, perhaps even to start attempting communication. But here's where the mystery deepens, where the question becomes not just fascinating but profound. If such a probe exists, if it's been here all along, watching and waiting, why hasn't it revealed itself to us in an unmistakable way? Why hasn't it landed on the White House lawn, or transmitted a clear message that says, "Hello, we've been waiting for you to grow up enough to have this conversation. The answer might be more subtle and more beautiful than we imagine. Consider the possibility that the probe is programmed with what we might call a prime directive, a rule that prevents it from interfering with our natural development. Just as anthropologists try to observe isolated human cultures without disrupting them, perhaps this probe is designed to watch without interfering, to let us develop at our own pace, to make our own mistakes and discoveries. It might be recording everything, creating an epic documentary of a species coming of age, data that will someday be transmitted back to its creators or their descendants, assuming they still exist after all this time. Or perhaps the probe is trying to communicate, but we simply don't know how to listen yet. We assume that an alien intelligence would use radio waves or some other form of electromagnetic radiation that we understand. But what if they're using something else entirely? What if they're manipulating gravitational waves in ways we can barely detect, or using quantum entanglement in ways we haven't even theorized yet, or encoding messages in the seemingly random impacts of cosmic rays on our atmosphere? We might be like someone from the Middle Ages trying to understand a smartphone, lacking not just the technology but even the conceptual framework to understand what we're looking at. There's also the possibility, both humbling and oddly comforting, that we're simply not interesting enough yet to warrant direct contact. Perhaps the probe has seen thousands of civilizations rise and fall throughout the galaxy, and we haven't yet done anything that distinguishes us from all the others. We might need to pass certain milestones, achieve certain technological or social developments, before the probe deems us ready for contact. Maybe we need to establish a permanent presence on another planet, or solve our environmental problems, or achieve a certain level of global unity. The probe might be like a cosmic teacher, waiting for us to complete our homework before moving on to the next lesson. As you lie there, perhaps feeling your breathing becoming slower and more regular, your mind beginning to drift like a boat on calm water, I want you to imagine what it would be like to be that probe. You've travelled for millions of years through the cold darkness of interstellar space. Your creators long since evolved into something unrecognizable or perhaps extinct altogether. You arrive at a young star system, full of planets and possibilities. You settle into wait, running on the barest trickle of power, most of your systems dormant, and then, after eons of patience, you detect the first stirrings of intelligence on the third planet from the Sun. You begin to observe more closely, recording everything, watching as this young species takes its first tentative steps toward the stars. What would you think of us, viewing us with the detachment of vast time and distance? Would you see our wars and conflicts as growing pains, necessary steps in our evolution? Would our art and music and literature seem like the beautiful flowering of consciousness, worth preserving and sharing with whoever sent you? Would you be touched by our curiosity, our relentless desire to understand the universe despite our limitations? Or would you simply record it all without judgment, a neutral observer documenting another chapter in the endless story of life in the cosmos? The search for such probes isn't just science fiction anymore. Real scientists with real funding are beginning to look for them. They're examining asteroids that behave strangely, objects in unusual orbits, anything that might be more than it appears. They're analysing old astronomical data, looking for objects that appeared and disappeared mysteriously, or that change course in ways that natural objects shouldn't. They're even considering the possibility that some of the UFO sightings that have puzzled observers for decades might be glimpses of these probes, though this remains highly controversial in the scientific community. One of the most intriguing aspects of the Bracewell probe hypothesis is that it solves some of the problems with other approaches to finding extraterrestrial intelligence. The famous Fermi paradox asks, if the universe is so vast and old, and if life is not impossibly rare, where is everybody? Why haven't we detected obvious signs of alien civilizations? Well, if civilizations primarily explore through robotic probes rather than radio signals or massive engineering projects, they might be much harder to detect. The galaxy could be full of these silent sentinels, each one waiting for its particular trigger, its moment to reveal itself. Think about our own exploration of space. We've sent probes to every planet in our solar system, and two of them, Voyager 1 and Voyager 2, have actually left the solar system and entered interstellar space. They carry golden records with sounds and images from Earth, messages for anyone who might find them millions of years from now. In a sense, we've already created our own Bracewell probes, primitive as they might be. If we, a species that has only been technological for a few centuries, have already done this, imagine what a species with millions of years of technological development might achieve. The probes they send might be so advanced that they seem like magic to us. They might be able to repair and upgrade themselves using materials they find in whatever star system they visit. They might be able to manufacture copies of themselves, spreading throughout the galaxy like seeds on the wind. They might contain vast libraries of information about their creators and their civilization, waiting to share this knowledge with anyone mature enough to receive it. They might even contain the uploaded consciousnesses of their creators, digital beings sleeping through the eons until they find someone to talk to. As we contemplate these possibilities, it's natural to feel a mix of emotions. There's excitement at the thought that we might not be alone, that somewhere in our solar system might be proof that intelligence has arisen elsewhere in the universe. There's perhaps a touch of anxiety about what such a discovery might mean for humanity, for our religions and philosophies and our sense of our place in the cosmos. But more than anything, I hope you feel wonder, that same wonder that has driven humans to explore and discover since we first looked up at the stars and wondered what they were. The night sky above us, whether we can see it clearly or not, is full of mysteries. Each point of light represents a sun, many of them with planets of their own, worlds we can barely imagine. And somewhere among all those stars, perhaps many somewheres, intelligence has arisen and looked out at the universe with the same wonder we feel. Perhaps they've sent their emissaries to find us, patient probes that even now might be watching, waiting, recording our story. As your consciousness begins to drift towards sleep, like a leaf floating gently down a quiet stream, I want you to hold on to this thought. We live in a universe of infinite possibilities. Every night when we sleep, every morning when we wake, we exist in a cosmos that might be teeming with intelligence, with civilizations beyond our imagination, with mysteries waiting to be discovered. The Bracewell probe that might be hiding in our solar system is just one possibility among countless others, but it's a possibility that reminds us how much we still have to learn, how much wonder still awaits us. In the coming chapters of our journey tonight, we're going to explore this possibility more deeply. We'll look at where such a probe might be hiding, what signs it might have left of its presence, and what it might mean for humanity if we were to discover it. We'll travel together through the vastness of space and time, always with this sense of gentle wonder, never with fear or anxiety, but with the calm curiosity that befits explorers of the cosmic mystery. For now, though, as this first chapter draws toward its close, I want you to simply rest with the possibility. Somewhere out there, perhaps closer than we think, an ancient artifact drifts through space, carrying messages from a civilization we've never met. It's been waiting for us since before we existed, patient as only a machine can be, ready to bridge the gap between worlds when the time is right. What stories might it tell? What knowledge might it share? What questions might it answer? And what new questions might it raise? These are the thoughts that will carry us forward into the vast territories we're about to explore together. The universe is speaking to us in whispers and hints, in anomalies and mysteries, in the strange behavior of objects we don't quite understand. Perhaps one of those whispers is from a Bracewell probe, waiting for us to learn its language, to recognize it for what it is. And perhaps, just perhaps, that moment of recognition is closer than we think. As we prepare to move deeper into this cosmic mystery, let yourself relax even further. Feel the weight of your body settling into comfort, your breathing becoming even more regular and peaceful. We have hours ahead of us to explore these ideas, to wander through the possibilities like explorers in a vast and beautiful garden. There's no rush, no urgency, just the gentle flow of contemplation and wonder that will carry us through the night. The universe, as we continue our gentle exploration tonight, is almost incomprehensibly vast, and it's in understanding this vastness that we begin to truly appreciate why the idea of Bracewell probes makes so much sense. As you settle deeper into comfort, perhaps adjusting your position slightly to find that perfect spot where your body feels completely supported and at ease, I want to take you on a journey through space and time to help you feel in your bones just how enormous the cosmos really is, and why this enormity makes the patient, eternal waiting of robotic probes perhaps the most logical way for civilizations to explore the galaxy. Let's begin with something familiar, something we can all relate to, the Earth itself. Our beautiful blue marble, as the astronauts call it, is about 12,700 kilometers in diameter. That might seem large, and indeed, if you were to walk around the equator at a steady pace without stopping, it would take you about a year to complete the journey. But in cosmic terms, Earth is tiny, a mere speck of dust floating in an endless void. The Moon, our nearest celestial neighbour, is about 384,000 kilometers away. Light, the fastest thing in the universe, takes about 1.25 seconds to travel from Earth to the Moon. When you look up at the Moon tonight, if you can see it, you're seeing it as it was 1.25 seconds ago. You're literally looking back in time, but the Moon is practically in our backyard compared to the other planets in our solar system. Mars, when it's closest to Earth, is still about 55 million kilometers away. Light from Mars takes between 3 and 22 minutes to reach us, depending on where both planets are in their orbits. When our rovers on Mars send back pictures, those images have already aged by the time we see them. We're always looking at Mars' past, never its present. This time delay, this gulf between worlds, even in our own solar system, gives us just a tiny taste of the true vastness of space. Jupiter, the giant of our solar system, is on average about 778 million kilometers from the Sun. When we look at Jupiter through a telescope, we're seeing it as it was about 43 minutes ago. Saturn, with its beautiful rings, is even farther, about 1.5 billion kilometers from the Sun. the light from Saturn takes about 80 minutes to reach us. By the time we get to Neptune, the most distant of the major planets, we're talking about 4.5 billion kilometers from the Sun, and light takes about 4 hours to make the journey. Now, these distances are already mind-boggling, already so vast that our human brains struggle to truly comprehend them. But here's where it gets truly staggering. All of these distances, everything I've just described, our entire solar system from Mercury to Neptune and beyond, is nothing more than a tiny island in an ocean of emptiness that stretches to the nearest star. If our solar system were a house, the nearest star would be another house about 4.5 kilometers away, with nothing but empty space in between. Proxima Centauri, that nearest star, is about 40 trillion kilometers away from us. That's 40 followed by 12 zeros. Light from Proxima Centauri takes 4.2 years to reach us. When we look at that star, we're seeing it as it was during whatever you were doing 4 years ago. If you sent a radio message to Proxima Centauri right now, and if someone there immediately sent a reply, you wouldn't receive it for 8.5 years. A conversation with even our nearest stellar neighbour would take nearly a decade per exchange. And Proxima Centauri is the closest star. Most stars are much, much farther away. The beautiful bright star Sirius, the brightest star in our night sky, is 8.6 light-years away. Vega, another bright star that was once our North Star and will be again in about 12,000 years, is 25 light-years away. When you look at Vega, you're seeing light that left that star when you were 25 years younger, or perhaps before you were even born. The star Polaris, our current North Star, is about 433 light-years away. The light you see from Polaris tonight began its journey to your eyes sometime in the late 1500s, when Shakespeare was writing his plays and Galileo was first turning his telescope to the heavens. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars, each one potentially hosting planets, each one a possible home for life. The galaxy itself is about 100,000 light-years across. If you could somehow travel at the speed of light, it would take you 100,000 years to cross from one side to the other. The ancient light from stars on the far side of our galaxy has been travelling since before modern humans evolved. We're seeing those stars as they were when Neanderthals still walked the Earth, and our galaxy is just one among billions. The Andromeda Galaxy, our nearest large galactic neighbour, is about 2.5 million light-years away. When we look at Andromeda, which you can actually see with the naked eye on a clear, dark night as a faint, fuzzy patch in the constellation of the same name, we're seeing it as it was 2.5 million years ago when our ancestors were just beginning to use stone tools. The light that left Andromeda when it looked the way we see it now has been travelling through empty space for longer than our species has existed. The observable universe, the part of the universe we can see because light has had time to reach us since the Big Bang, is about 93 billion light-years in diameter. It contains at least 2 trillion galaxies, each with hundreds of billions of stars. The numbers become meaningless at this scale, so vast that they're just abstractions. But each of those galaxies is real. Each of those stars is a sun perhaps warming planets will never see, and on some of those planets, perhaps many of them, life has arisen and looked out at the same vast cosmos we're contemplating tonight. Now, in all this vastness, in all this emptiness punctuated by islands of matter and energy, how do civilizations find each other? How do they communicate? How do they explore? The distances are so vast that even at the speed of light, which as far as we know is the absolute speed limit of the universe, it would take years, centuries, millennia, or longer to travel between stars. A civilization on a planet orbiting a star 1,000 light-years away could send us a radio message, but by the time we received it, decoded it, and sent a reply, 2,000 years would have passed. The civilization that sent the original message might not even exist anymore. This is why the idea of Bracewell probes is so elegant, so practical despite seeming like science fiction. Instead of trying to have a conversation across these impossible gulfs of space and time, a civilization sends a probe, a patient robotic explorer that doesn't mind taking millions of years to reach its destination. The probe carries within it all the information needed for first contact, perhaps even the ability to have real-time conversations once it arrives. It's like sending a letter instead of trying to shout across an ocean, except the ocean is billions of times wider and the letter might take millions of years to arrive. Think about the journey such a probe would make. Launched from some distant world, perhaps when our sun was still forming from a cloud of gas and dust, it would accelerate slowly, patiently, using technologies we can barely imagine. Perhaps it would use a solar sail, riding the pressure of starlight like a sailing ship rides the wind. Perhaps it would use ion propulsion, expelling charged particles to create thrust, efficient but slow, perfect for a journey measured in geological time. Or perhaps it would use something we haven't discovered yet, some property of space or matter that allows for more efficient travel between the stars. For most of its journey, the probe would drift through the perfect darkness of interstellar space. Out there between the stars, the darkness is absolute in a way we can't experience on Earth. There's no air to scatter light, no nearby sun to illuminate anything. The temperature is just a few degrees above absolute zero, colder than anything on Earth. The probe would be more isolated than anything we can imagine, farther from anything else than we can comprehend. Years would pass, then decades, then centuries, then millennia, with nothing changing, nothing happening, just the slow drift through the void. But the probe wouldn't mind. It has no consciousness in the way we understand it. Or perhaps it does, but it sleeps through the journey, its electronic dreams undisturbed by the passage of time. It's patient in a way biological beings could never be. It doesn't get lonely or bored. It doesn't worry about the meaning of its existence or wonder if its creators still remember it. It simply continues on its path, following the gravitational pull of distant stars, making tiny course corrections when necessary, waiting for the moment when it will arrive at its destination. And then, after a journey that might have lasted longer than any human civilization has existed, it would begin to detect the gravitational pull of our sun growing stronger. It would sense the solar wind, the stream of charged particles our sun constantly emits. Its sensors, dormant for so long, would begin to wake up, to take measurements, to look for planets. And there, third from the sun, it would find Earth, a blue and white jewel covered in water and clouds, showing clear signs of life in the oxygen of its atmosphere and the green of its continents. The probe might spend years or decades studying our solar system before choosing where to position itself. It would map all the planets, catalogue the asteroids, measure the solar wind and magnetic fields. It would look for the best place to wait, somewhere stable, somewhere it could remain for millions of years if necessary. waiting for intelligence to arise on that promising third planet. And then it would settle in to wait some more, because waiting is what it was built to do. Consider the patience required for such a mission. The civilization that sent the probe would know they would never see the results. Their son might die before the probe reached its destination. Their entire species might evolve into something unrecognizable or go extinct entirely. But still they would send it, because the drive to explore, to reach out, to make contact with other minds in the cosmos is perhaps a universal trait of intelligence. They would send it as a gift to the future, a message to civilizations not yet born, a hand extended across the vastness of space and time. This vast emptiness between the stars, this crushing isolation that would drive any biological being mad, is actually perfect for preserving information. In interstellar space there's no weathering, no erosion, no oxidation. A probe could drift for billions of years and remain essentially unchanged. The golden records we put on the Voyager spacecraft will last for billions of years in interstellar space, far longer than any artifact we've left on Earth. If an alien civilization finds one of the Voyagers in 1 billion years, the record will still be playable, our voices and music still preserved in those golden grooves. So, a Bracewell probe arriving in our solar system millions of years ago would still be functional today, its messages still intact, its system still ready to activate when the right conditions are met. It would be like a time capsule, but one that can open itself when it judges the time is right. And that time might be now, as we begin to reach out into space ourselves, as we begin to listen for signals from other civilizations, as we begin to seriously contemplate our place in the cosmic community. The vastness of space that seems like such a barrier to communication and travel actually makes Bracewell probes more likely, not less. Because the distances are so great, because real-time communication is impossible, because biological beings can't easily travel between the stars, robotic probes become the obvious solution. They're the message in a bottle thrown into the cosmic ocean, drifting on currents of gravity and time until they wash up on the shores of another world. As you lie there, perhaps feeling yourself drifting deeper into relaxation, you're breathing slow and steady like the patient pulse of a distant pulsar. Imagine yourself as one of these probes, drifting through the vastness between worlds. You have all the time in the universe. There's no rush, no urgency. You're carrying precious cargo, information about a civilization that wanted to say hello across the cosmos, and you'll deliver that message whenever the time is right, whether that's tomorrow or 1 million years from now. The vastness that separates us from other stars, other worlds, other civilizations might seem lonely and isolating, but it's also full of potential. Every cubic meter of that seeming emptiness could contain a probe we haven't detected yet. Every unusual asteroid, every strange orbit, every unexplained observation could be a hint that we're not alone, that someone somewhere sent a message our way long before we were ready to receive it. The vastness is not empty, it's full of possibilities, full of patience, full of messages waiting to be discovered. In our next chapter, we'll explore more deeply the specific ideas of Ronald Bracewell, the scientist who first proposed this hypothesis, and understand why his idea has captivated scientists and dreamers for over 60 years. But for now, as you drift in the vastness of your own consciousness, approaching the shores of sleep like a probe approaching a distant star system, remember that the universe's great distances are not barriers but bridges, not walls but invitations to find new ways to connect across the cosmic dark. In 1960, while the world was caught up in the space race and the Cold War, a brilliant mind at Stanford University was thinking far beyond the immediate concerns of Earth, contemplating questions that stretched across cosmic time and space. Ronald Newbold Bracewell was his name, and though you might not have heard of him before tonight, his ideas have profoundly shaped how we think about the search for extraterrestrial intelligence. As you continue to relax, perhaps feeling the gentle weight of sleep beginning to tug at the edges of your consciousness, let me tell you about this remarkable man and the elegant hypothesis that bears his name. Bracewell was born in Sydney, Australia, in 1921, and from an early age he showed a fascination with mathematics and the physical world that would define his entire life. He was the kind of person who looked at the stars not just with wonder, but with questions, always questions, about how things worked and what might be possible. During World War II, he worked on radar development, helping to perfect the technology that would later prove crucial in radio astronomy. After the war, he moved to England to study at Cambridge, where he worked with some of the greatest minds in physics and astronomy, before eventually settling at Stanford University in California, where he would spend the rest of his career pushing the boundaries of our understanding of the cosmos. It was at Stanford in the late 1950s and early 1960s that Bracewell began to think seriously about the problem of interstellar communication. This was an exciting time in the search for extraterrestrial intelligence. In 1959, Giuseppe Cocconi and Philip Morrison had published a groundbreaking paper in the journal Nature, suggesting that if extraterrestrial civilizations existed, they might be broadcasting signals at the frequency of neutral hydrogen, a universal constant that any technological civilization would know about. In 1960, Frank Drake conducted Project Ozma, the first systematic search for alien radio signals, pointing a radio telescope at two nearby sun-like stars and listening for any signs of intelligent transmission. But Bracewell, always the creative thinker, wondered if there might be a better way. Radio signals, he reasoned, face enormous challenges when travelling between the stars. They spread out as they travel, becoming weaker with distance according to the inverse square law. A signal that starts out powerful enough to be easily detected becomes a whisper by the time it crosses interstellar space. Moreover, there's the problem of timing. A civilization would have to be broadcasting at exactly the right time for us to detect them, and we would have to be listening at exactly the right frequency, pointing our telescopes in exactly the right direction. The odds of everything aligning perfectly seemed vanishingly small. So Bracewell proposed an alternative, an idea so elegant and practical that it seems obvious in retrospect, though it was revolutionary at the time. Instead of trying to communicate across the vast distances of space using electromagnetic radiation, why not send physical probes to other star systems? These probes would be like automated ambassadors, carrying all the information needed for first contact and capable of waiting as long as necessary for a technological civilization to arise and discover them. He called them interstellar communication relays, though they've since become known as Bracewell probes in his honour. The beauty of Bracewell's idea lies in its solution to multiple problems simultaneously. First, there's the problem of signal strength. A radio signal weakens dramatically over interstellar distances, but a probe, once it arrives at its destination, can transmit at whatever power level is appropriate for local communication. It's like the difference between trying to shout to someone on another continent versus walking over to them and having a normal conversation. Second, there's the problem of timing. A probe can wait indefinitely for the right moment to make contact, monitoring the target planet for signs of technological development and choosing the optimal time to reveal itself. Bracewell imagined these probes as being incredibly sophisticated, far beyond anything we could build with 1960s technology, but perhaps achievable for a civilization with centuries or millennia more technological development than us. They would need to be self-repairing, able to maintain themselves over geological timescales, using materials found in whatever star system they visited. They would need powerful artificial intelligence, capable of making complex decisions about when and how to make contact without any guidance from their creators, who might be extinct by the time the probe reached its destination. They would need to be patient beyond any human understanding of patience, willing to wait millions of years if necessary for the right conditions to arise. In his original paper, published in Nature in 1960, Bracewell laid out a specific scenario for how such a probe might operate. It would enter a star system and position itself in a stable orbit, perhaps at one of the Lagrange points where gravitational forces balance out. It would monitor the electromagnetic spectrum for signs of technological activity. Once it detected radio or television broadcasts indicating the presence of a technological civilization, it would wait a bit longer to ensure the civilization was stable and advancing, not about to destroy itself. Then, when the time was right, it would announce its presence. The announcement, Bracewell suggested, might come in a clever and unmistakable way. The probe might record some of our own television or radio broadcasts and transmit them back to us with a delay of a few seconds or minutes. Imagine the shock and wonder if we suddenly started receiving our own broadcasts from space, clearly coming from a source within our solar system, but not from any human spacecraft. It would be an elegant calling card, using our own signals to say, "Hello, I'm here, I've been listening, and I'd like to talk." Once contact was established, the probe could serve as a repository of information about its creators and their civilization. It might contain libraries of scientific knowledge, histories of other worlds, philosophies and art from across the galaxy. It could answer our questions about the universe, about other civilizations, about technologies we haven't yet imagined. It would be like having a wise teacher from the stars, patient and knowledgeable, ready to guide us into the larger cosmic community. But Bracewell also considered more subtle possibilities. What if the probe was programmed not to reveal itself immediately, but to study us first, to learn about our languages, our cultures, our level of technological and social development? It might spend decades or centuries observing before making contact, ensuring that we were truly ready for the knowledge it carried. This period of observation might be happening right now, with the probe watching our internet traffic, our satellite communications, our scientific publications, building a comprehensive understanding of human civilization before deciding how best to approach us. The probe might also be programmed with what we would now call a prime directive, a rule against interfering with the natural development of a civilization. It might be designed to observe only, to record the story of our species for some vast galactic archive, never revealing itself at all. In this scenario, the probe would be like a cosmic naturalist, documenting the rise of intelligence on Earth without disturbing it, preserving our authentic development for future study. Bracewell even considered the possibility that probes might be designed to reproduce themselves using materials found in the star systems they visit. A single probe arriving in our solar system might use asteroids or moon material to build copies of itself, which would then be sent on to other star systems. In this way, a single civilization could explore the entire galaxy with self-replicating probes, even if the original civilization no longer existed. The galaxy might be full of these mechanical descendants of long-dead civilizations, still carrying out their programming, still searching for new life and new civilizations. The implications of Bracewell's hypothesis extend far beyond just the search for extraterrestrial intelligence. If such probes are possible, and if even a small fraction of technological civilizations build them, then they should be relatively common in the galaxy. The fact that we haven't definitively detected one yet might tell us something important about the nature of intelligence in the universe, or about our own limitations in searching for them, or perhaps about the extreme subtlety with which they're designed to operate. Think about how our own technology has advanced since Bracewell first proposed his hypothesis. In 1960, the most sophisticated computers filled entire rooms and had less processing power than the phone in your pocket today. We hadn't yet landed humans on the moon, hadn't sent probes to the outer planets, hadn't developed the internet or GPS or any of the thousands of technologies we now take for granted. If we've come this far in just 60 years, imagine what we might achieve in 600 years, or 6,000, or 6 million. The probes that seemed like pure science fiction in Bracewell's time now seem increasingly plausible. In fact, we're already taking the first steps toward building our own Bracewell probes. Projects like Breakthrough Starshot are planning to send tiny probes to Proxima Centauri using light sails pushed by powerful lasers. These probes would be simple compared to what Bracewell envisioned, but they would be a start. They would take about 20 years to reach Proxima Centauri and could send back images and data about any planets they find there. It's not hard to imagine that in a few centuries we might be able to send much more sophisticated probes, perhaps even probes capable of the kind of patient waiting and intelligent decision-making that Bracewell described. The search for Bracewell probes has become a legitimate scientific endeavour. Astronomers have looked for artificial objects at the Earth-Sun and Earth-Moon Lagrange points. They've examined unusual asteroids that might be camouflage probes. They've searched for radio signals coming from within our solar system that can't be explained by natural phenomena. So far, nothing definitive has been found, but the search has really only just begun. Our solar system is vast, with millions of asteroids and comets, any one of which could be something more than it appears. One of the most intriguing aspects of Bracewell's hypothesis is that it changes how we think about time in the search for extraterrestrial intelligence. Instead of needing to be lucky enough to exist at the same time as a broadcasting civilization, and to be listening at just the right moment, we only need to find the probes that might have been sent millions of years ago. These probes are like messages in bottles that don't decay, time capsules that can wait forever if necessary. They transform the search from one that requires precise temporal coincidence to one that accumulates probability over vast stretches of time. As you drift deeper into relaxation, perhaps feeling your thoughts becoming more fluid and dreamlike, consider the profound optimism embedded in the Bracewell hypothesis. Any civilization that would build and send such probes must believe in the future, must believe that intelligence and consciousness are precious enough to seek out wherever they might arise, must believe that communication and connection across the cosmos are worth enormous effort and patience. they must be civilizations that have survived their own technological adolescence, overcome whatever challenges threaten their existence, and emerged with the wisdom and capability to reach out across the galaxy. The probes themselves, if they exist, are monuments to hope and curiosity. Each one represents a civilization's desire to not be alone, to find others who look up at the stars with wonder, to share knowledge and perhaps wisdom across the vast darkness. They're like seeds of connection scattered through the galaxy, waiting for the right conditions to grow into relationships between worlds. Bracewell himself continued to work on radio astronomy and the search for extraterrestrial intelligence until his death in 2007. He lived to see many of his ideas taken seriously by the scientific community, to see the search for extraterrestrial intelligence grow from a fringe pursuit to a legitimate scientific discipline. He saw the discovery of exoplanets, worlds orbiting other stars, confirming that planetary systems are common in the galaxy. He saw the development of technologies that made his probes seem less like fantasy and more like eventual reality. In his later years, Bracewell remained optimistic about the possibility of contact. He believed that the galaxy was likely full of intelligence, that we were not alone, and that eventually, whether through radio signals or probes or some method we haven't yet imagined, we would make contact with our cosmic neighbours. He saw the search itself as valuable, regardless of the outcome, because it forced us to think about our place in the universe, about what it means to be intelligent, about what we would want to say if we had the chance to introduce ourselves to the galaxy. The Bracewell hypothesis remains one of the most elegant and practical solutions to the problem of interstellar communication. It acknowledges the vast scales of space and time that separate civilizations while offering a way to bridge those gaps. It recognizes that patience, not speed, might be the key to exploring the galaxy. And it suggests that right now, as you lie there listening to these words drifting towards sleep, there might be an ancient probe somewhere in our solar system, waiting with infinite patience for the moment when humanity is ready to receive its message. Our solar system, as familiar as it might seem with its 8 planets and their moons that we've studied since childhood, is actually a vast and largely unexplored wilderness, full of hiding places where a Bracewell probe could have been waiting for millennia or even millions of years. As you continue to relax, perhaps feeling the boundaries between wakefulness and sleep beginning to blur like the edge of a nebula, let me paint you a picture of just how many places there are in our cosmic neighborhood where an alien artifact could remain hidden, watching, waiting, perhaps even trying to communicate in ways we haven't yet recognized. Let's begin with the sheer number of objects in our solar system. We tend to think of it as mostly empty space with a few planets, but this is far from the truth. Between Mars and Jupiter lies the asteroid belt, containing millions of rocky bodies ranging from tiny pebbles to the dwarf planet Ceres, which is nearly 1,000 kilometers across. Current estimates suggest there are over 1 million asteroids larger than 1 kilometer in diameter, and hundreds of millions smaller than that. Any one of these could be a camouflaged probe, its surface covered with dust and regolith accumulated over eons, indistinguishable from a natural asteroid to our telescopes. Think about how perfect an asteroid would be as a disguise for a probe. Asteroids come in all shapes and sizes, some nearly spherical, others elongated or oddly shaped. An artificial object could easily hide among them without arousing suspicion. Some asteroids are solid rock, others are loosely bound piles of rubble, and still others are rich in metals, a probe could position itself among the metallic asteroids, where its own metal construction wouldn't seem out of place. It could even hollow out a natural asteroid and hide inside, protected from cosmic rays and micrometeorite impacts by a shell of natural rock. We've only closely examined a tiny fraction of the asteroids in our solar system. As of tonight, we've sent spacecraft to visit fewer than 20 asteroids up close, and we've only landed on a handful. That leaves millions unexplored, each one a potential hiding place for something extraordinary. Even the asteroids we have photographed from a distance have only been seen from one angle, at one moment in time. An object on the far side of an asteroid, or hidden in a crater, or buried beneath the surface, would remain completely invisible to us. Beyond the main asteroid belt, there are other populations of small bodies that could harbour hidden probes. The Trojan asteroids share Jupiter's orbit, clustered at the L4 and L5 Lagrange points, 60 degrees ahead and behind the giant planet. These are gravitationally stable regions where objects can remain for billions of years with minimal energy expenditure. There are thousands of known Trojan asteroids and probably hundreds of thousands we haven't discovered yet. A probe positioned among them would be in an ideal location to monitor the inner solar system while remaining in a stable long-term orbit. Then there are the Lagrange points themselves, those special locations where the gravitational forces of two large bodies balance out, creating areas where objects can maintain their position relative to both bodies with minimal fuel use. Every planet has 5 Lagrange points with respect to the Sun, and the Earth-Moon system has its own set of 5. These points would be ideal parking spots for a probe. The Earth-Sun L4 and L5 points in particular would offer a stable vantage point from which to observe Earth while remaining at a constant distance. Scientists have actually searched some of these Lagrange points for alien artifacts, but the searches have been limited. Space is vast, and even at a Lagrange point, a probe could be millions of kilometers from where we're looking and still be at the same point in a gravitational sense. It's like searching for a particular grain of sand on a beach when you don't even know what color the grain is or if it's on the surface or buried. Our searches so far have been preliminary at best, barely scratching the surface of what's out there. Moving farther out in the solar system, we encounter the realm of the gas giants and their dozens of moons. Jupiter alone has 79 known moons, Saturn has 82, Uranus has 27, and Neptune has 14. Many of these moons are tiny, just a few kilometers across, and we know almost nothing about them beyond their orbits. A probe could easily masquerade as a small moon, or it could land on one of the larger moons and establish a base there. The far sides of these moons, the hemispheres that always face away from their planets, would be particularly good hiding spots shielded from Earth's telescopes by the moons themselves. Consider Europa, Jupiter's ice-covered moon that likely harbours a liquid ocean beneath its frozen surface. If a probe wanted to study potential life in our solar system, Europa would be a fascinating target. The probe could have drilled through the ice long ago, sending submersible explorers into the dark ocean below, studying whatever might swim in those alien waters. From Earth, we would see nothing but the same icy surface we've always seen, unaware of the alien presence beneath. Or think about Titan, Saturn's largest moon, with its thick atmosphere and lakes of liquid methane. A probe on Titan's surface would be hidden beneath clouds so thick that we can barely see through them, even with our best instruments. It could have been there for millions of years, studying the complex organic chemistry that makes Titan so intriguing to astrobiologists. When the Cassini spacecraft dropped the Huygens probe onto Titan in 2005, it could have landed within kilometers of an alien artifact, and we might never have known. Beyond the realm of the giant planets lies the Kuiper Belt, a vast region of icy bodies extending from Neptune's orbit out to about 50 astronomical units from the Sun. This region contains hundreds of thousands of objects larger than 100 kilometers across and millions of smaller ones. We've discovered only a tiny fraction of them. Pluto, which we didn't even get a good look at until the New Horizons flyby in 2015, is just one of many large objects in the Kuiper Belt. Each of these distant, frozen worlds could be harboring secrets we can't imagine. The Kuiper Belt would be an excellent location for a probe that wanted to observe our solar system, while minimizing the chance of accidental discovery. Out there, in the cold and dark, a probe could operate for billions of years, its electronics kept naturally cool, its solar panels or nuclear power source providing just enough energy to maintain its vigil. It could watch the inner solar system through powerful telescopes, recording the rise and fall of life on Earth, waiting for the emergence of intelligence. Even farther out, perhaps a light year or more from the Sun, lies the hypothetical Oort cloud, a spherical shell of icy bodies that serves as the source of long-period comets. The Oort cloud might contain trillions of objects, from tiny ice particles to bodies hundreds of kilometers across. We've never directly observed an object in the Oort cloud. We only infer its existence from the comets that occasionally fall toward the inner solar system. If a probe wanted to remain completely hidden while still being technically within our solar system, the Oort cloud would be the perfect location. But perhaps the most intriguing possibility is that a probe might not be hiding at all. It might be something we've already discovered and catalogued, but haven't recognized for what it truly is. Throughout the history of astronomy, we've found objects that behave in ways we don't fully understand. Some asteroids have unusual orbits that are hard to explain through natural processes alone. Some objects reflect light in strange ways or rotate in patterns that seem oddly regular. We always assume these anomalies have natural explanations, and usually we're right. But what if, just once, we're wrong? Take, for example, the case of 1991 VG, a small near-Earth object discovered in November 1991. This object, only about 10 meters across, had an orbit remarkably similar to Earth's, and it exhibited a rapid variation in brightness that suggested it was rotating quickly or had a highly reflective surface. Some astronomers speculated that it might be an old rocket booster returning to Earth's vicinity, but no mission could be identified as its source. Others suggested it might be a natural asteroid, but its orbit was unusually Earth-like for a natural object. A few brave souls even suggested it might be an alien probe, though this idea was never taken seriously by the mainstream scientific community. 1991 VG passed by Earth and disappeared back into the darkness, and we still don't know exactly what it was. Or consider Oumuamua, which we'll explore in more detail in a later chapter, the interstellar object that passed through our solar system in 2017. Its elongated shape, its unexpected acceleration, and its unusual properties sparked serious scientific debate about whether it might be artificial. While most scientists believe it was a natural object, the fact that serious researchers even considered the possibility of it being an alien artifact shows how difficult it can be to distinguish between the natural and the artificial when dealing with objects we can barely see. there's also the fascinating possibility that a probe might be hidden in plain sight right here on Earth. If a probe arrived millions of years ago before humans evolved, it might have landed on Earth to study the development of life up close. Over geological time, it could have been buried by sediment, covered by vegetation, or sunk into the ocean. It might be sitting at the bottom of the Mariana Trench, or buried beneath Antarctic ice, or hidden in a cave system we haven't explored. The Earth is vast, and we've explored only a tiny fraction of it in detail. Some researchers have even suggested we should look for alien artifacts on the Moon. The Moon's lack of atmosphere and geological activity means that objects on its surface can remain unchanged for billions of years. If a probe landed on the Moon millions of years ago, it would still be there today, perhaps covered by a thin layer of dust but otherwise intact. The Moon would be an ideal location for a probe to monitor Earth, close enough to observe in detail but far enough away to avoid accidental discovery. When the Apollo astronauts explored the Moon, they covered only a tiny area, equivalent to exploring an area the size of a small park and declaring you've explored all of Earth. The search for hidden probes has led to some interesting scientific endeavours. The SETA program, Search for Extraterrestrial Artifacts, specifically looks for alien artifacts in our solar system. Researchers have proposed various search strategies, from examining astronomical photographs for objects that appear and disappear, to looking for infrared signatures that might indicate waste heat from alien technology, to searching for radio signals originating from within our solar system rather than from distant stars. Some scientists have suggested that we should pay special attention to objects that seem to be in unusually convenient locations for observing Earth. An object at the Earth's Sun L4 or L5 point, for instance, would always maintain the same angle relative to Earth and the Sun, making it ideal for long-term observation. An object in a highly elliptical orbit that regularly brings it close to Earth might be performing periodic detailed surveys. An object in a retrograde orbit, moving opposite to the direction of the planets, might have positioned itself that way to stand out when we're finally sophisticated enough to notice. The challenge of finding a hidden probe is compounded by the fact that we don't know what we're looking for. Would an alien probe be large or small? Would it be active or dormant? Would it be trying to remain hidden or attempting to attract our attention? Would it look artificial to us? Or would millions of years of cosmic weathering make it indistinguishable from a natural object? These unknowns make the search incredibly difficult, like trying to find something when you don't know what it looks like, where it might be, or even if it exists at all. But perhaps that's part of the test. Maybe a truly advanced civilization would hide their probe in such a way that finding it requires us to reach a certain level of technological and intellectual sophistication. The probe might be hidden in plain sight, but in a way that we can only recognize once we've developed the right tools or the right way of thinking. It might be waiting for us to prove ourselves worthy of contact by being clever enough to find it. As you lie there, perhaps feeling yourself drifting like a small boat on a vast calm ocean, think about all these hiding places in our solar system. Right now, as you listen to these words, there might be an ancient probe orbiting silently among the asteroids, or sitting on a frozen moon of Neptune, or drifting through the Kuiper belt. It might have been watching when the dinosaurs ruled the Earth, recording their extinction when the asteroid struck. It might have observed the first humans learning to use tools, building cities, developing technology. It might be watching us right now, patient and silent, waiting for the right moment to reveal itself. The idea that something could be hidden in our solar system, something that's been there all along, watching and waiting, transforms our familiar cosmic neighborhood into a place of mystery and possibility. Every asteroid becomes potentially significant, every unusual orbit potentially meaningful, every unexplained observation potentially historic. We live in a solar system that we've barely begun to explore, full of places where secrets might be hiding, where patience might be rewarded with the greatest discovery in human history. The universe is never truly quiet. Even in the vast emptiness between stars, there's a constant whisper of electromagnetic radiation, a cosmic static that fills every corner of space with its ancient song. As you settle deeper into relaxation, perhaps noticing how your breathings become slow and rhythmic like the pulse of a distant quasar. Let me tell you about the mysterious signals we've detected over the years, signals that have made scientists pause and wonder, signals that might, just might, be the calling cards of Bracewell probes, trying to announce their presence to a civilization that's finally ready to listen. Radio waves are everywhere, passing through your body right now as you lie there, invisible and unfelt, carrying information from countless sources both natural and artificial. The cosmos is full of natural radio sources, pulsars spinning like cosmic lighthouses, sending out beams of radiation with clockwork precision, distant galaxies with supermassive black holes at their centers, screaming radio waves into the void as they devour matter. The background hiss left over from the Big Bang itself, the cosmic microwave background that fills all of space with its faint whisper of creation. Among all this natural noise, how would we recognize an artificial signal, especially one from a probe that might be using communication methods we've never imagined? The story of mysterious signals begins long before we were actively searching for them. In 1967, a graduate student named Jocelyn Bell Burnell was analysing data from a new radio telescope in Cambridge, England, when she noticed something odd. There was a signal that appeared every night at the same point in the sky, pulsing with incredible regularity every 1.337 seconds. The signal was so regular, so precise, that at first she and her advisor, Anthony Hewish, thought it might be interference from human technology. But as they studied it more carefully, they realized it was coming from deep space, far beyond our solar system. The signal was so strange, so unlike anything they'd seen before, that they initially labeled it LGM-1 for Little Green Men. Could this be it, they wondered, the first detection of an alien civilization? As it turned out, they had discovered pulsars, rapidly rotating neutron stars that emit beams of radiation like cosmic lighthouses. It was a natural phenomenon, but one so strange and unexpected that even trained astronomers initially considered the possibility of artificial origin. This experience taught us something important. The universe is capable of producing signals that seem artificial but aren't, and distinguishing between the natural and the artificial can be extraordinarily difficult. But then, on August 15th, 1977, something happened that still sends shivers down the spines of those who study it. At the Big Ear Radio Telescope at Ohio State University, astronomer Jerry Eman was reviewing data when he saw a signal so strong, so unusual, that he circled it on the printout and wrote "Wow" in the margin. The wow signal, as it came to be known, lasted for 72 seconds, the exact length of time an extraterrestrial signal would be expected to last as the telescope's beam swept across its source due to Earth's rotation. The signal was at 1420 MHz, very close to the hydrogen line frequency that scientists had predicted would be ideal for interstellar communication. It was narrow band, meaning it was concentrated in a small frequency range, unlike natural sources that tend to be broadband. It was 30 times stronger than the background noise, impossible to miss or misinterpret, and most mysteriously, it never repeated. Despite numerous attempts to detect it again, pointing telescopes at the same spot in the constellation Sagittarius, the signal was never heard again. What was the WOW signal? Theories abound, but none are entirely satisfactory. Some suggest it was a reflection of an Earth-based signal off a piece of space debris, but the frequency and characteristics don't match any known terrestrial transmissions from that time. Others propose it was a previously unknown natural phenomenon, perhaps a rare type of cosmic event we haven't encountered again. But there's another possibility, one that aligns perfectly with the Bracewell probe hypothesis. What if it was a probe's attempt to get our attention? A single powerful broadcast designed to make us look, to make us wonder, to make us search. Think about it from the probe's perspective. It's been waiting for millions of years, monitoring Earth for signs of technological development. It detects our radio telescope scanning the sky and decides the time has come to announce its presence. But it doesn't want to be too obvious, doesn't want to disrupt our natural development. So it sends a single, powerful signal, something that will make us take notice but won't prove anything definitively. It's like tapping someone on the shoulder and then stepping back to see how they react. The probe might be waiting to see if we're sophisticated enough to recognize the significance of what we've detected, patient enough to keep searching, wise enough to prepare ourselves for contact. In recent years, we've detected other mysterious signals that have sparked similar debates. Fast radio bursts, or FRBs, are millisecond-long bursts of radio waves that appear to come from distant galaxies. First discovered in 2007, these bursts release as much energy in a millisecond as the Sun does in 80 years. Most appear to be one-off events, never repeating, though a few have been observed to repeat in patterns we don't fully understand. The natural explanation for FRBs involves magnetars, highly magnetized neutron stars, or perhaps colliding compact objects like black holes or neutron stars. But some of their properties are puzzling. Some FRBs show signs of being dispersed by passing through plasma, allowing us to estimate their distance, and many appear to be coming from billions of light-years away. But what if some of them aren't that distant? What if some are much closer, perhaps even within our own galaxy or solar system, their signals crafted to mimic distant natural phenomena while actually being attempts at communication? In 2019, astronomers detected a repeating FB that showed a regular pattern. 4 days of activity followed by 12 days of silence, repeating like clockwork. This 16-day cycle was unlike anything seen in other FRBs and suggested some kind of orbital mechanism. While scientists proposed natural explanations involving binary star systems or precessing magnetars, the regularity of the pattern was striking. Could it be a beacon, broadcasting on a schedule, waiting for someone to notice the pattern and respond? There have been other strange signals too, less famous than the WOW signal, but equally puzzling. In 2003, astronomers detected GCRTJ 1745-3009, a radio source near the centre of our galaxy that brightened dramatically for about 10 minutes, 5 times over the course of 7 hours, then disappeared. The signals were highly polarized and showed characteristics unlike any known type of astronomical object. Despite extensive follow-up observations, the source has never been detected again. In 2016, Russian astronomers detected a strong signal from the direction of HD 164595, a Sun-like star about 94 light-years away known to have at least one planet. The signal was detected by the Ratan 600 radio telescope and was strong enough that, if artificial, it would require the power output of an entire Type II civilization on the Kardashev scale. The discovery wasn't announced for over a year, and when other telescopes looked for the signal, they found nothing. Was it interference, a natural phenomenon, or something else entirely? But perhaps we're looking for the wrong kind of signals. A Bracewell probe, with potentially millions of years of technological advancement behind it, might communicate in ways we haven't thought of. It might modulate gravitational waves, creating ripples in space-time itself that we're only just beginning to detect with instruments like LIGO and Virgo. It might use neutrinos, those ghostly particles that pass through matter almost without interacting, as a communication medium. It might manipulate quantum entanglement in ways we haven't yet discovered, sending information instantaneously across any distance. Or perhaps the probe is already communicating with us, but we don't recognize it as communication. Those strange, fast radio bursts might contain encoded information that we haven't figured out how to decode. The seemingly random cosmic ray strikes that occasionally flip bits in our computers might not all be random. The unusual isotope ratios in some meteorites might be signatures left by probes processing materials in our solar system. We might be surrounded by messages we don't know how to read, like someone illiterate sitting in a library. Consider the possibility that a probe might be testing us, sending signals of increasing complexity to gauge our technological and intellectual development. The wow signal might have been a simple beacon, a basic hello to see if anyone was listening. When we didn't respond, perhaps because we couldn't, the probe might have moved on to more complex signals, embedding information in ways that would only be detectable once we reached a certain level of sophistication. There's also the intriguing possibility that some of the signals we attribute to natural sources might actually be artificial. Pulsars, for instance, are so regular, so precise, that they were initially thought to be artificial. What if some of them are? What if an advanced civilization can engineer neutron stars, turning them into galactic beacons? What if some of the gamma-ray bursts we detect, those massive explosions that briefly outshine entire galaxies, are actually industrial accidents or deliberate signals from Type III civilizations that harness the energy of entire galaxies? The search for artificial signals has become increasingly sophisticated. Projects like SETI at home have enlisted millions of volunteers to analyze radio telescope data on their home computers, searching for patterns that might indicate artificial origin. The Breakthrough Listen project is conducting the most comprehensive search ever undertaken, observing thousands of nearby stars and dozens of nearby galaxies across a wide range of radio and optical frequencies. Machine learning algorithms are being developed to recognize patterns that human analysts might miss, to find signals hidden in the noise. But what if the signals aren't hidden at all? What if they're right in front of us, obvious and unmistakable, but we're not ready to see them? There's a concept in psychology called inattentional blindness, where people fail to notice obvious things when their attention is focused elsewhere. The famous invisible gorilla experiment showed that people watching a video of basketball players often completely miss a person in a gorilla suit walking through the scene. Perhaps we're so focused on looking for certain types of signals that we're missing others that are right in front of us. The static of the universe, that constant background hiss of natural radio waves, might be like an ocean that occasionally carries messages in bottles to our shore. Some of these messages might be from Bracewell probes, patient sentinels that have been trying to get our attention for decades or centuries or longer. Each mysterious signal we detect, each anomaly we can't quite explain, might be another tap on the shoulder, another attempt to make us look up from our daily concerns and realize we're not alone. As you drift deeper into relaxation, perhaps feeling yourself floating in that comfortable space between waking and sleeping, imagine yourself as a radio telescope, sensitive to the faintest whispers from space. In your relaxed state, you might be more receptive to possibilities, more open to ideas that seem fantastic in the harsh light of day. Somewhere out there, perhaps closer than we think, a probe might be broadcasting right now, its signals spreading out like ripples on a cosmic pond, waiting for someone to notice, to understand, to respond. The signals in the static remind us that the universe is full of mysteries, full of things we don't understand. Every unexplained burst of radio waves, every anomalous signal, every pattern we can't quite explain, adds to the growing body of evidence that the cosmos is stranger and more wonderful than we imagine. Whether these signals come from natural phenomena we haven't discovered yet, or from artificial sources trying to communicate with us, they remind us to keep listening, to keep searching, to keep our minds open to possibilities that might transform our understanding of our place in the universe. In our next chapter, we'll explore one of the most intriguing objects ever to visit our solar system, an interstellar visitor that sparked serious scientific debate about whether we had finally found evidence of alien technology. But for now, as you rest in the comfortable darkness behind your closed eyelids, remember that the universe is speaking to us constantly in languages we're only beginning to learn. Every signal carries information, every pattern has meaning, and somewhere in all that cosmic noise might be the message that changes everything, waiting patiently for us to learn how to hear it. In October of 2017, something extraordinary happened that would forever change how we think about visitors from beyond our solar system, something that would spark serious scientific debate about whether we had finally encountered evidence of alien technology. As you continue your journey into peaceful contemplation, perhaps feeling the gentle pull of sleep growing stronger with each passing moment, let me tell you about Oumuamua, the mysterious object that came from interstellar space, behaved in ways we didn't expect, and left us with more questions than answers. The story begins at the Haleakala Observatory in Tiwanaku, Hawaii, where astronomer Robert Rarick was reviewing images from the Pan-STARRS telescope, a powerful instrument designed to scan the sky for potentially hazardous asteroids that might threaten Earth. On October 19th, he noticed something unusual, an object moving through the images in a way that suggested it was travelling extraordinarily fast, too fast to be bound by the sun's gravity. After checking and rechecking the calculations, the conclusion was inescapable. This object had come from outside our solar system, the first interstellar visitor we had ever detected. The object was given the name Oumuamua, a Hawaiian word meaning scout, or messenger from afar arriving first, a name that would prove eerily appropriate as scientists began to study its properties. At first, it seemed like it might be a fairly ordinary comet or asteroid that just happened to come from another star system. But as more observations came in, Oumuamua began to reveal characteristics that defied easy explanation, characteristics that would lead some serious scientists to propose that it might be artificial. The first surprise was Oumuamua's shape. Based on how its brightness varied as it tumbled through space, astronomers calculated that it was highly elongated, perhaps 10 times longer than it was wide. This would make it shaped something like a cigar or a pancake, depending on which models you believed, unlike any asteroid or comet we'd ever seen in our own solar system. The most elongated asteroids we knew of were maybe 3 times longer than they were wide, but Oumuamua was far more extreme. It was as if someone had designed an object to be as un-asteroid-like as possible, while still being able to pass as one from a distance. Then came an even bigger surprise. As Oumuamua moved away from the Sun, astronomers noticed that it was accelerating slightly more than it should be based on gravity alone. This kind of acceleration is common in comets, which release jets of gas as ice sublimes in the Sun's heat, acting like tiny rocket engines. But here's the strange thing, Oumuamua showed no signs of outgassing. No coma of gas and dust surrounded it. No tail streamed behind it. None of the typical signs of a comet were present. Yet it was accelerating as if pushed by some invisible force. The scientific community was puzzled. Various explanations were proposed for the anomalous acceleration. Maybe Oumuamua was made of some exotic type of ice that sublimed without creating visible gas. Maybe it was so small and the outgassing so minimal that we simply couldn't detect it with our instruments. Maybe the solar radiation pressure, the tiny push from sunlight itself, was responsible, though this would require Oumuamua to be extraordinarily thin and light, like a cosmic sail. It was this last possibility that caught the attention of Avi Loeb, the chair of Harvard's astronomy department, and one of the most respected astrophysicists in the world. In a paper that sent shockwaves through the scientific community, Loeb and his colleague Shmuel Bialy calculated that for solar radiation pressure to account for Oumuamua's acceleration, it would need to be less than 1 millimeter thick, essentially a flat sheet travelling through space. Such an object seemed unlikely to form naturally, leading them to suggest, quite seriously, that Oumuamua might be artificial, perhaps a piece of alien technology, maybe even a light sail from another civilization. Think about this for a moment, letting the implications settle into your relaxing mind like sediment in still water. A light sail is a propulsion technology that we humans have only recently begun to experiment with, using the pressure of light itself to push a spacecraft through space. It's elegant, requiring no fuel, capable of eventually reaching very high speeds. If an alien civilization wanted to send probes to other star systems, light sails would be one of the most efficient ways to do it. And here was Oumuamua, behaving exactly as a light sail would behave, tumbling through our solar system like a piece of cosmic flotsam from some distant shipwreck. Loeb's suggestion was controversial, to say the least. Many of his colleagues disagreed, some quite vehemently. They argued that we shouldn't jump to artificial explanations when natural ones, however unlikely, were still possible. They pointed out that we'd only had a few weeks to observe Oumuamua before it became too faint to see. Not nearly enough time to gather all the data we would need to determine its true nature. They worried that suggesting Oumuamua might be artificial would damage the credibility of the search for extraterrestrial intelligence. But Loeb persisted, and his arguments were hard to dismiss entirely. He pointed out that Oumuamua's trajectory had brought it through the local standard of rest, the average velocity of stars in our neighbourhood, as if it had been parked there, waiting for a star system to come along. He noted that of all the possible shapes for a naturally occurring object, the thin sheet required to explain Oumuamua's acceleration by solar radiation pressure was extraordinarily unlikely. He argued that we should be open to the possibility of artificial origin, especially given how unusual Oumuamua's properties were. The debate over Oumuamua became a fascinating window into how science grapples with extraordinary possibilities. On one side were those who argued for caution, for sticking with natural explanations until they were definitively ruled out. On the other were those who said we should seriously consider all possibilities, including artificial origin, especially when the natural explanations required their own set of unlikely assumptions. It was a debate not just about one strange object, but about how we approach the search for extraterrestrial intelligence, and how open we should be to evidence that doesn't fit our expectations. As Oumuamua continued its journey, out of our solar system, moving too fast for any of our spacecraft to catch up with it, astronomers scrambled to learn as much as they could from the limited observations they had. They discovered that Oumuamua was reddish in colour, similar to some objects in the outer solar system, suggesting its surface had been exposed to cosmic rays for a very long time, perhaps millions or billions of years. They confirmed that it was tumbling in a complex pattern, rotating around its long axis about every 7 or 8 hours. They searched for radio emissions that might indicate it was artificial, but found only silence. The silence itself raised questions. If Oumuamua was a Bracewell probe or some other kind of alien technology, why wasn't it transmitting? Perhaps it was a derelict, a piece of dead technology that had been drifting through space for eons, its power source long exhausted, its computers long silent. Or perhaps it was transmitting, but in a way we couldn't detect, using technologies we haven't discovered yet. Or maybe it was simply observing, gathering data about our solar system to transmit back to its creators when it was safely away from our detection. Some scientists proposed that Oumuamua might be exactly what we would expect a Bracewell probe to look like after millions of years in interstellar space. The elongated shape might be the result of erosion by cosmic dust, wearing away at the probe like wind and water carving a stone into a streamlined shape. The tumbling might indicate that its stabilization systems had failed long ago. The lack of obvious signals might mean its communication systems were damaged, or that it was designed to remain silent until certain conditions were met. There's another intriguing possibility that connects Oumuamua directly to the Bracewell probe hypothesis. What if Oumuamua wasn't the probe itself, but a messenger sent by a probe already in our solar system? Imagine a Bracewell probe that has been watching Earth for millions of years, hidden among the asteroids or moons. It detects that we've developed the technology to spot interstellar objects. It wants to test our reactions, to see how we respond to something unusual. So it manufactures or redirects an object to pass through the inner solar system in a way that we'll notice, exhibiting properties that will make us wonder, make us debate, make us think about the possibility of extraterrestrial intelligence. The timing of Oumuamua's discovery is itself interesting. We detected it just a few years after we developed the technological capability to spot such objects. The Pan-STARRS telescope that found Oumuamua had only been fully operational since 2014. It's as if Oumuamua arrived just when we were ready to see it. Though, of course, this could be pure coincidence. Or perhaps there have been many interstellar visitors over the years that we simply didn't have the technology to detect. And Oumuamua was just the first one we happened to catch. In the years since Oumuamua's visit, astronomers have been eagerly searching for more interstellar objects. In 2019, they found Tua/Borisov, clearly a comet with a visible coma and tail, behaving exactly as we would expect a natural interstellar comet to behave. This discovery was both exciting and somewhat disappointing. Exciting because it showed that interstellar objects might be relatively common, but disappointing because Borisov was so clearly natural, lacking the mysteries that made Oumuamua so intriguing. The contrast between Oumuamua and Borisov actually strengthens the case for Oumuamua being unusual. If Borisov represents what a typical interstellar object looks like, then Oumuamua's strange properties become even harder to explain through natural processes. It's like finding two messages in bottles on a beach. One is clearly just a bottle that happened to wash ashore, while the other has properties that make you wonder if someone deliberately sent it your way. As you lie there, perhaps feeling your thoughts becoming more fluid and dreamlike, imagine what it would have been like to be on Oumuamua during its passage through our solar system. If it was indeed artificial, what instruments might it have carried? What data might it have collected? Did it photograph Earth, recording our civilization at this particular moment in history? Did it sample the solar wind, analyze the sun's spectrum, map the positions of all our planets? Is that data now travelling back to its creators, wherever and whenever they might be? The question of what Oumuamua was may never be definitively answered. It's already too far away for our telescopes to see, and it's moving too fast for any spacecraft we could build with current technology to catch up with it. But in a way, the mystery itself is valuable. Oumuamua has forced us to think seriously about what an alien artifact might look like, how we would recognize it, and how we should respond if we find one. It's shown us that the scientific community can have serious substantive debates about the possibility of extraterrestrial technology without descending into pseudoscience or sensationalism. The Oumuamua question has also inspired new research and new missions. Scientists are developing better ways to detect and track interstellar objects, hoping to spot the next one earlier and observe it for longer. There are proposals for spacecraft that could be launched quickly to intercept future interstellar visitors, to study them up close and perhaps even return samples to Earth. The European Space Agency's Comet Interceptor mission, planned for launch in 2029, will wait in space for an interesting target, ready to spring into action when the next Oumuamua comes along. Some researchers have suggested that we should be looking for more Oumuamuas, not just in real-time observations but in historical data. Perhaps other interstellar objects have passed through our solar system in recent decades, recorded in astronomical photographs but not recognized for what they were. By applying modern analysis techniques to old data, we might find evidence of previous visitors that we missed at the time. There's also the possibility that Oumuamua-like objects might be common, perhaps even artificially produced and distributed throughout the galaxy like dandelion seeds on the cosmic wind. If advanced civilizations use light sails for interstellar travel, then broken or discarded sails might drift through space indefinitely, occasionally passing through star systems like ours. the galaxy might be littered with the technological debris of civilizations that explored the stars millions or billions of years ago. The philosophical implications of Oumuamua are profound, regardless of whether it was natural or artificial. If it was natural, it shows us that interstellar space is full of objects we've never seen before, materials and structures that don't exist in our solar system, expanding our understanding of what's possible in the universe. If it was artificial, it would be the most important discovery in human history, proof that we're not alone, that intelligence has arisen elsewhere and achieved interstellar technology. But perhaps the most important lesson from Oumuamua is about keeping an open mind. The universe is vast and ancient, full of possibilities we haven't imagined. Objects like Oumuamua remind us that we've barely begun to explore even our own cosmic neighborhood, that surprises await us in the darkness between the stars. They remind us to look carefully at anomalies, to question our assumptions, to be ready for discoveries that might challenge everything we think we know. As Oumuamua continues its journey through interstellar space, tumbling through the darkness at 26 kilometers per second, it carries with it the questions it raised during its brief visit to our solar system. Was it just an unusual rock, shaped by eons of cosmic erosion into a form we didn't expect? Was it a piece of alien technology, either a deliberate probe or accidental debris? Was it a natural phenomenon of a type we haven't seen before, teaching us something new about how objects form and evolve in interstellar space? We may never know the answer, but the question itself has value. It's made us think, made us wonder, made us look more carefully at the universe around us. And perhaps that was the point all along. If Oumuamua was a Bracewell probe or a test sent by one, it succeeded in its mission. It made us pay attention, made us debate and discuss, made us more aware of the possibility that we're not alone. It prepared us in a way for the next strange visitor, the next anomaly, the next piece of evidence that the universe is stranger and more wonderful than we imagine. Time, as you drift deeper into this peaceful state of contemplation, takes on a different quality when we consider the vast scales on which the universe operates, and perhaps more importantly, the scales on which ancient civilizations might think and plan. As humans, we tend to think in terms of years or decades, occasionally centuries when we're being particularly forward-thinking. But what if there are intelligences out there that think in terms of millions or billions of years, for whom the entire history of human civilization is just a brief flicker, a single frame in a cosmic movie that has been playing since before our sun was born? This perspective, this deep time view of intelligence and civilization, fundamentally changes how we think about Bracewell probes and the search for extraterrestrial intelligence. If you're a civilization that has survived for millions of years, that has overcome whatever challenges threaten young technological species, that has achieved a kind of cosmic maturity we can barely imagine, then sending out probes that might take millions of years to reach their destinations and millions more to report back isn't an insurmountable challenge. It's just patience on a scale that matches the universe itself. Consider for a moment the age of our galaxy, the Milky Way. It's approximately 13 billion years old, formed not long after the universe itself began. The first stars in our galaxy were massive and short-lived, fusing hydrogen into heavier elements and then exploding as supernova, seeding space with the materials needed for planets and life. The second generation of stars formed from this enriched material could have had rocky planets like Earth. Some of these second-generation stars formed 10 billion years ago, when the universe was only 3 or 4 billion years old. Now think about what this means for the potential age of civilizations in our galaxy. If life arose on a planet orbiting one of these older stars, and if it followed a similar evolutionary timeline to life on Earth, then intelligent civilizations could have emerged billions of years before Earth even formed. These ancient civilizations would have had billions of years to develop technology, to explore the galaxy, to send out probes to every star system they could reach. From their perspective, our solar system would be a relatively young neighborhood, a recent development in the ongoing story of the galaxy. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicating extraterrestrial civilizations in our galaxy. The equation includes factors like the rate of star formation, the fraction of stars with planets, the fraction of planets where life develops, and crucially, the length of time civilizations release detectable signals into space. This last factor, often called L, might be the most important. If civilizations typically destroy themselves shortly after developing technology, then L is small, and we're likely alone, or nearly alone in the galaxy. But if some civilizations learn to survive to overcome the challenges that threaten young technological species, then L could be enormous, millions or billions of years. A civilization that has survived for millions of years would have a fundamentally different perspective on existence than we do. They would have seen stars born and die, watched planets form and evolve, perhaps witnessed the rise and fall of countless other civilizations. They would think in geological and astronomical timescales the way we think in terms of seasons and years. For them, waiting 1,000,000 years for a probe to reach a distant star would be like us waiting a few months for a package to arrive from overseas. Such ancient civilizations might have transcended biology entirely, uploading their consciousness into artificial substrates that don't age, don't die, don't get impatient. They might exist as pure information, patterns of data in vast computer networks, experiencing subjective time at whatever rate they choose. For them, the millions of years it takes for light to cross the galaxy might pass in what feels like moments, or they might slow their subjective time to match the cosmic pace, experiencing the universe as a slow, stately dance of stars and galaxies. The probe such civilizations would send out would reflect this long-term thinking. They wouldn't be designed for quick missions lasting years or decades, but for odysseys lasting eons. They would be built to endure not just the vacuum and radiation of space, but the slow degradation that comes with time itself. They would need to be self-repairing, able to fix damage from micrometeorite impacts and cosmic ray strikes. They might even be designed to evolve, to adapt to conditions they encounter, to upgrade themselves using materials and energy sources they find along the way. These probes might be programmed with extraordinary patience, willing to wait not just for intelligence to evolve, but for it to reach specific milestones. Perhaps they're waiting for us to achieve certain technological capabilities, like fusion power or quantum computing. Perhaps they're waiting for us to reach certain social milestones, like ending war or achieving global cooperation on existential challenges. Or perhaps they're waiting for us to demonstrate certain philosophical or ethical developments, to show that we're ready to join a galactic community without being a threat to ourselves or others. The concept of patience on these scales is almost incomprehensible to humans. We get frustrated waiting a few minutes for a web page to load. Yet these probes might be programmed to wait millions of years without any sign of impatience or degradation of purpose. They would be like seeds that can remain dormant indefinitely, ready to sprout when conditions are finally right, even if those conditions don't arise for geological ages. Think about the implications of this for the Bracewell probe hypothesis. A probe that arrived in our solar system when dinosaurs roamed the Earth would have waited 65 million years to see us emerge. That seems like an impossibly long time to us, but for a probe designed by a billion-year-old civilization, it might be perfectly reasonable. The probe might have observed the entire history of mammalian evolution, watching our ancestors develop from small nocturnal creatures to the dominant form of life on the planet, eventually developing the intelligence and technology to potentially detect the probe itself. Such long-term observation would provide incredibly valuable scientific data. Imagine the insights into evolution, into the development of intelligence, into the factors that allow life to flourish or cause it to struggle. A probe that has been watching Earth for millions of years would have data on mass extinctions, climate changes, the movement of continents, the evolution of countless species. It would be an unparalleled record of a living planet, information that might be precious to civilizations trying to understand the universal principles of life and intelligence. The probe might also be part of a vast network, one node in a galactic surveillance system that has been growing for billions of years. Each probe would gather data about its local star system, and periodically, perhaps every few million years, they might share information with each other, building a comprehensive picture of how the galaxy changes over time. This network might track the birth and death of stars, the formation of planets, the emergence of life, the rise and fall of civilizations. It would be a kind of galactic library, preserving the history of countless worlds. From this perspective, the apparent silence of the universe, the Fermi paradox that asks, where is everybody? Zerenia might have a different explanation. Perhaps ancient civilizations don't communicate using methods we can detect because they don't need to. Their probes form a network that shares information in ways we haven't discovered yet, perhaps using quantum entanglement or gravitational waves, or some physics we haven't even theorized. They might be talking all around us, but in a language we don't yet know how to hear. The patience of these ancient intelligences might extend to their approach to younger civilizations like ours. They might have observed thousands of species reaching our current level of development, and they might have learned that interference, even well-intentioned, often does more harm than good. So they wait, they watch, they record, but they don't intervene. They let each species find its own path, make its own mistakes, achieve its own victories. It's the ultimate expression of patience, allowing events to unfold over centuries and millennia without interference. This long-game approach might also explain why we haven't seen obvious signs of advanced civilizations in the galaxy. If they think in terms of billions of years, they might take a very conservative approach to expansion and resource use. Instead of rapidly colonizing every available star system, they might expand slowly, carefully, ensuring they don't disrupt existing ecosystems or potential future civilizations. They might have divided the galaxy into zones, preserving some regions as wilderness, where life can evolve naturally, while developing others for their own purposes. Consider the possibility that our solar system is in one of these preserved zones, a kind of cosmic nature reserve where life is allowed to develop without interference. The Bracewell probe, if it exists, might be like a hidden camera in a nature documentary, recording our development for the interest and education of countless other species. We might be living in a kind of galactic zoo, though one so vast and naturalistic that we don't even realize we're being observed. The technological capabilities of civilizations playing this long game would be almost magical by our standards. They would have had millions or billions of years to perfect their technology, to discover new laws of physics, to engineer matter and energy in ways we can't imagine. Their probes might be made of materials we haven't discovered, powered by energy sources we don't understand, operating on principles that would seem to violate the laws of physics as we know them. Yet despite their vast superiority, these ancient civilizations might still find young species like us interesting, even valuable. We represent something they can never be again, new, fresh, seeing the universe with wonder for the first time. Our art, our music, our unique perspective on existence might be treasured by beings that have seen everything else the galaxy has to offer. We might be like children to them, naive and sometimes foolish, but also creative and surprising in ways that being with millions of years of experience no longer can be. As you lie there, feeling perhaps the way time seems to slow and stretch as you approach sleep, you're experiencing a tiny taste of what these long-lived intelligences might experience all the time. In your relaxed state, minutes can feel like hours, or hours can pass in what seems like moments. Time becomes fluid, subjective, malleable. Now imagine extending that feeling across millions of years, experiencing the rise and fall of civilizations the way you might experience the changing of seasons. The search for Bracewell probes takes on a different character when we consider these vast timescales. We shouldn't expect to find a probe that was sent recently, or one that's in a hurry to make contact. Instead, we should look for something ancient, patient, weathered by eons in space, but still functional, still waiting. It might be covered in cosmic dust, scarred by billions of micrometeorite impacts, its original surface long since eroded away. But inside, protected by whatever advanced technology created it, its computers still function, its sensors still observe, its patience still infinite. The probe might have been waiting so long that the civilization that sent it has evolved into something unrecognizable, or perhaps ceased to exist entirely. It might be following programming written in a language that no living being remembers, pursuing goals that made sense millions of years ago but might seem arbitrary now. It might be like a message in a bottle, where both the sender and the intended recipient are long gone, but the message itself persists, waiting for someone, anyone, to find it and read it. This raises profound questions about the nature of intelligence and purpose. What drives a civilization to send out probes that won't report back for millions of years? What kind of beings think in such vast timescales? Are they still biological, or have they transcended biology? Are they still individuals, or have they merged into some kind of collective consciousness? Are they still curious about the universe, or have they seen so much that nothing surprises them anymore? Perhaps the answer is that intelligence, wherever it arises, shares certain universal traits. Curiosity might be one of them, the desire to explore and understand. The wish to communicate, to know that you're not alone, might be another. And perhaps patience, the ability to work toward goals that won't be achieved in your lifetime, or even in the lifetime of your species, is a mark of true cosmic maturity. The Bracewell probes, if they exist, would be monuments to these traits, carrying the curiosity and hope of ancient civilizations across the vast darkness between the stars. As we continue to search for these probes, we're not just looking for alien technology. We're looking for evidence of patience on a cosmic scale, of planning that spans geological ages, of hope that endures across eons. We're looking for proof that intelligence can survive its technological adolescence and achieve something like immortality. Not for individuals, but for the curiosity and wonder that defines consciousness itself. As you drift in this peaceful space between waking and sleeping, let your mind wander into one of humanity's most profound questions. What would it actually be like if we discovered a Bracewell probe? If we made contact with an intelligence from beyond Earth? Not the dramatic Hollywood version with massive ships hovering over cities, but the real thing, perhaps quiet, subtle, gradually dawning on us like understanding slowly emerging from confusion. The reality of first contact through a Bracewell probe might be far stranger and more wonderful than our fiction has imagined, unfolding not in days or weeks, but perhaps over years or decades as we slowly learn to communicate with an intelligence that has been waiting patiently for this moment since before our species existed. Imagine it beginning not with fanfare but with puzzlement, a gradual accumulation of anomalies that don't quite fit our understanding of how things should work. Perhaps astronomers notice that an asteroid's orbit has changed slightly, not dramatically, just enough to be statistically significant. They check their calculations, run the numbers again, look for gravitational perturbations that might explain it, but nothing quite fits. Then they notice that the change in orbit has brought the asteroid into a position where it's easier to observe from Earth, as if it wanted to be seen more clearly. Or perhaps it starts with radio astronomers detecting a signal that seems to be coming from within our solar system, but from no known spacecraft or natural source. The signal is weak at first, barely distinguishable from the cosmic background noise, but it has a structure to it, a mathematical pattern that no natural phenomenon should produce. It might be prime numbers, or the Fibonacci sequence, or the digits of pi, something that says, this is artificial, this is intentional, this is meant for you to notice. The scientific community would react with extreme caution, at first, as they should. Extraordinary claims require extraordinary evidence, and the claim that we've detected an alien probe would be the most extraordinary claim in human history. There would be endless verification, checking and rechecking of the data, looking for any possible natural explanation or human error. Scientists would be desperate to avoid another faster-than-light neutrino situation, where an apparent breakthrough turned out to be a measurement error. But let's say the evidence holds up. Multiple independent observations confirm that something unusual is happening. The signal continues, perhaps growing stronger or more complex over time. The orbital changes continue in ways that can't be explained by known physics. Slowly, reluctantly, the scientific community would have to confront the possibility that they're observing something artificial, something not of human origin. The process of disclosure would be delicate and complex. There would be intense debates about when and how to inform the public. Some would argue for immediate transparency, that humanity has a right to know. Others would worry about panic, about the collapse of financial markets, about religious and social upheaval. Governments would be involved, intelligence agencies, the United Nations. There would be leaks, rumours, conspiracy theories mixing with facts in a confused jumble of information and misinformation. But perhaps the probe, if it's been watching us as long as we imagine, would understand our social dynamics and reveal itself gradually in a way designed to minimize disruption. It might start by communicating only with scientists, sending messages that require significant expertise to decode, ensuring that the news spreads slowly through academic channels before reaching the general public. It might gauge our reactions at each stage, adjusting its approach based on how we respond. The first real communication might be mathematical, the universal language that any technological civilization must understand. The probe might send increasingly complex mathematical proofs, starting with simple arithmetic and building up to advanced concepts. It would be testing us, determining our level of mathematical sophistication, establishing a common ground for more complex communication. Mathematicians around the world would work together to decode and respond to these messages, humanity's first homework assignment from an alien intelligence. As communication develops, the probe might move on to physics, chemistry, biology, gradually building a shared vocabulary of scientific concepts. It might send diagrams of atoms, molecules, DNA, establishing that it understands our physical nature. It might describe its own construction, the materials and technologies it uses, though much of it might be beyond our current understanding. We would be like students in a cosmic classroom, struggling to understand lessons from a teacher whose knowledge vastly exceeds our own. The emotional impact on humanity would be profound and varied. For some, it would be a dream come true, validation of their belief that we're not alone, that the universe is full of intelligence and wonder. For others, it would be terrifying, a threat to their worldview, their religion, their sense of human specialness. There would be celebration and denial, wonder and fear, hope and despair, all mixed together in a complex global emotional response. Religious communities would grapple with the theological implications. Some would see the probe as confirmation of divine creation on a cosmic scale, God's intelligence manifest throughout the universe. Others might struggle to reconcile the existence of alien intelligence with human-centric religious doctrines. New religions might spring up around the probe, viewing it as a messenger from advanced beings who have achieved something like godhood through technology. The probe might anticipate these reactions and try to address them. It might send messages emphasizing that its creators were once like us, young and confused and searching for meaning. It might share the spiritual and philosophical insights of its civilization, not to replace our beliefs, but to add to the great conversation about existence and purpose that all conscious beings engage in. It might be careful to present itself not as a superior being dictating truth, but as a fellow traveller in the cosmic journey, just one that happens to be much older and more experienced,